In the last few videos, what we've been looking at relates to motion. That is, how is the position, the speed, the velocity, acceleration, how they interlinked. Is there relative motion, constrained motion, and so on? But we never really cared about the forces, right? We were always looking at just some measured information that's provided to you, as in, here's the speed or here's the acceleration, and this is the constraint that exists and how it can move, then make some meaningful uh, analysis and then come to something useful. That was kind of what we've been studying. If you look at the very beginning, that is what we had defined as a geometry of motion. So we're ignoring the forces and the moments. Let's now look at kinetics, wherein we do look into what are the forces that are causing this kind of a motion, or what is the moment that is causing this motion. Okay, so this here is now the next module, that is kinetics. Of course, this has to do with Newton's laws. So when you try to recall without a Google search or opening a textbook, what are the first, the second, and the third laws? Go ahead and write it down yourself. Okay, so I hope these three laws require no real explanation. It's very familiar to you. The first one is related to inertia. It's gonna, an object is gonna stay at rest or continue to move with uniform velocity. That is, there's not going to be any change in the velocity, and velocity being a vector implies that it has to be in the same direction and same straight line at constant speed if there is no unbalanced force acting on it. Okay, so if it has to change direction, there must be some unbalanced force. If it has to decelerate, there must be some unbalanced force. If it's at rest, it stays at rest unless there is some unbalanced force that's going to cause it to move. The second one says the acceleration is proportional to the resultant force acting on it. This is essentially the key element of kinetics, wherein we start looking at all of the forces that are acting on it using a free body diagram. So if this here is your particle and you have these forces, so there is, I'm just drawing a bunch of forces. Essentially, all of these forces in the free body diagram, which I'm going to write as the sum of forces in the free body diagram. These are all vectors, so it's a vector sum. This is equal to the sum of forces in the kinetic diagram. What is the kinetic diagram? It is accounting for the inertia of the same object. So this here is the object, and these are all of the external forces. Now in the kinetic diagram, what you draw is your inertial force. That is the acceleration that it has. Let's say it's in this direction. So this is MA. This here is F1, F2, F3, F4, F5. You look at all of these forces. So there's F1, you add F2, you add F3, you add F4, you add F5. This here is your net force, right? This is your sum of forces in the free body diagram. This will be equal to this inertial force, which is mass times acceleration. Okay. And the third law, it says that the forces of action and reaction between interacting bodies are equal and opposite in magnitude. So if you have two bodies interacting in some way where this body is applying a force F on this body, then the other body is going to have an equal and opposite force generated that is going to act on this body. Okay. In kinetics, we're focusing on this. You're familiar with this, so let's get started. Um, this here is your question. Go ahead and try to solve this yourself. Of course, it's a great simplification in saying that all four tires contribute equally, and that the deceleration is constant. But this makes your problem solving easier. This here is a car over a distance of 50 meters. It comes to a stop. And initially it had a speed of 100 kilometers per hour. And finally it has a speed of 0. How do you find the acceleration here? It's given that deceleration is constant, so you can say v square minus u square is equal to 2as. Try to remind yourself, how do we derive this? It is from v dv is equal to a ds. And when you integrate it, you get v square minus u square is equal to 2as, only when a is constant. In this case, v is 0. U is 100 times 5 over 18, because you want to keep the units constant. Since here I'm doing 2a times 50 meters. From this, you get that the acceleration is minus 7.72 meters per second. Okay, so we have the acceleration. That means that we can have a kinetic diagram where we're drawing all of our inertial forces. So you'll have it in the opposite direction to motion. So it's in this way. You have mass that is 1,500 kgs times 7.72. This is your kinetic diagram. In your free body diagram, you are now drawing all of the forces. So there is a gravitational force of 1,500 g. There is a normal force, which is going to cancel out since there's no motion in the upward direction. And you have deceleration from the tires, so it's acting in this direction. You have 4 times the force of braking, okay, 4 FB. So what I'm saying now is that the sum of forces in the free body diagram is equal to sum of forces in the kinetic diagram. These are all vectors. So if I were to write it, you would have n minus 1,500 g along the j hat direction minus 4 FB along the I hat direction is equal to minus 1,500 times 7.72 I hat. And along the j hat direction, you get n minus 1,500 g is equal to 0, giving me the normal force is equal to 1,500 g. This is not asked, it's just an outcome of having this vector equation. You will have components along j hat and I hat. In the I hat direction, you have minus 4 FB is equal to minus 1,500 times 7.72, giving you the force of braking in one wheel is equal to 2,890 newtons. Okay, I hope that makes sense. It's actually much simpler to just solve it directly, but I wanted to show this as an example of your force balance and so on. Okay, let's now talk about the idea of friction. You must have heard of static and kinetic friction. If I were to now draw a graph where on the y-axis I have the magnitude of friction. Okay. And this here is your applied force. Okay, so starting at 0, when you have 0 applied force, how much is the friction? This here is your body. You have some force being applied, and there is some friction here. So you draw that. There is some friction, mu s for static, and mu k for kinetic friction. And you have some force F that you're applying. That is your applied force. This force is going to try and cause this body to move to the right. And friction is going to prevent any kind of relative motion between the surfaces in contact. So how would this graph look? In the beginning, your static friction is going to counteract your force F, and it's going to be equal and opposite. So it prevents that force from having any real effect. So there's going to be an angle of 45 degrees. This here is your static friction. I'm going to call it Fx. Well, I'm going to call it Fs. And then your static friction has a maximum value, which is given by Fs max. So until that static friction maximum value is provided by the applied force, the object remains at rest. After this point, kinetic friction takes effect, which drops the overall friction to some other lower value. And then you have this here as your kinetic friction. So it's usually drawn as a squiggly line because the kinetic friction will vary as the surface contact changes and so on, but that's not important. So this here is a kinetic friction region. Over here, the object starts to move. And over here, in this region, the object is stationary. Okay. So you know this relation here, this is your Fs max, that is whatever is your normal force between the object and the surface is resting on, that is the Fn, the normal force. Mus times that would be your maximum possible value of the friction. And kinetic friction will resist So in this case, the kinetic friction would be equal to mu k times Fn. Okay, let's do a problem now. So we have a block of 50 kgs on a surface. And given that this surface has mu s is equal to 0.5 and mu k is equal to 0.4, question asks you if this here is the net result of all your forces in the x direction, and there are none in the y direction, that at what Fx would the block begin to slide? It's simply an application of what we just discussed. I want the numeric value. Okay. I hope you're confident enough to do it yourself. You have this 50 kg, the 50 kg block. I'm drawing the free body diagram first. So we have 50 G acting downwards, and we have Fn acting in this way, and we have sigma Fx acting in this way. We know that this block has a tendency to move to the right, which means then that I would have friction acting in this way, given this F here. It's a free body diagram, and then here we have the kinetic diagram with mx double dot in this way. Wherein m is 50, so I can write that as 50x double dot. Now, according to Newton's second law, I have the sum of force in the free body diagram is equal to sum of forces in the kinetic diagram. So I have this sigma Fx acting to the right minus F along I hat plus Fn minus 50g along j hat is equal to 50x double dot I hat, which gives me that Fn minus 50g is equal to 0, or Fn is equal to 50g. And we have that Fs max is equal to Fn times mu s, which is 50 times g times mu s, which is given to you as 0.5, giving me a value of 250 newtons. Okay, so the question does ask you at what Fx will the block begin to slide. So that is when it has reached this point here, that is your Fs max. So your applied force is essentially this here sigma Fx in this case. As we're increasing it, once you reach this point here, it starts to slide. So if I can write it starts to slide. There's relative motion now. And because it says begins to slide, then that means that this x double dot is equal to 0. It's the limit. It's when it just starts to slide. Okay, so when it begins to slide, x double dot is equal to 0, giving me sigma fx is equal to f, well, I should say sigma fx minus f is equal to 0, wherein this f here is fs max, meaning sigma fx is equal to 250 newtons, which is the amount of force that you need to apply so the block begins to slide. So when sigma fx is greater than or equal to 250 newtons, the block slides. Okay, this is relatively easy. I hope that this makes sense. Let's now do the case where we no longer have it on a horizontal surface, but instead we have it on this slanted surface of an angle of 15 degrees. And I'm going to draw them this way because my app requires me to first draw it horizontally before I can rotate it. So I can get a nice rectangle. That's just this app that I'm using. Okay. There's again 50 kgs, and now we have a force of P acting on it, and it's acting up the slope. And we have different coefficients of static and kinetic friction. We have mu s is equal to 0.2, mu k is equal to 0.15. The question asks you to determine the acceleration for P is equal to 150 newtons, P is equal to 300 newtons, and P is equal to 0 newtons. Okay, so try solving this yourself. Remember that the nature of how friction behaves is nonlinear. It is not a continuously straight line. It is straight up to a certain point, after which it drops and then it's constant. Okay, this is how friction behaves. So try this yourself. It's an interesting problem. Okay, I'm going to do it myself. The first thing you got to figure out is what is Fs max? This is equal to mu s times Fn, where Fn is a normal force. What is that normal force? Let's find out. So I'm going to draw the free body diagram and the kinetic diagram. You have this P acting in this way. You have that along the slope, right? You have gravitational force that is 50g acting in this way. Then from the surface, you have a normal force acting in this way. Are there any other forces? Yes, there will be friction. But for now, I'm just looking at Fn. So if I were to try to find out what is Fn, I have to have the kinetic diagram as well defined. So in this case, let's say that it is something, let's say it's upward, so it's 50 x double dot, it's along the slope, right? So we can say from this is that if we were to balance the forces, there is no acceleration along the perpendicular to the slope, which means Fn minus the component of gravity in this direction should be equal to 0. So right here, where Fn minus, what is the component of this along this direction? Always be careful. Don't be in a hurry to define it. If this here is 15 degrees, and this would be 90 minus 15, and since this here is perpendicular, then this angle would be 90 minus 15, giving me an angle of 15 degrees here. Okay, so Fn minus 50g, what is the component here? 50g cos 15. So this gives me Fn is equal to 50g cos 15, that is 473.8 newtons. And we have Fs max is equal to mu s times of this. So mu s is given to you as 0.2, which is equal to 94.7 newtons. So this is your Fs max, which means that if your net force in this direction is greater than 94.7, then your static friction will be broken and become kinetic friction. Okay. So what is the net force that is acting upwards? I'm going to say that this here is x direction. Okay. So net force in the x direction, that is upward, this would be P minus 50g sine 15. Why is it sine? This here is 50g. This would be 50g sine 15. So in the upward direction, it is P minus that. Okay. And, essentially, it says that if this here greater than 94.7, it will slide. So let's now do the cases. We have case 1 where P is equal to 150 newtons, which means that the net force upwards is equal to 150 minus 50g sine 15, which is equal to, and if you plug in the numbers, you will get 23 newtons, which is less than 94.7 newtons, which means that your static friction will overcome this, and there is no motion. Okay. The second case, wherein P is equal to 300 newtons. Now in this case, your sum of forces upward is equal to 300 minus 50g sine 15. This is going to be equal to 173 newtons, which is greater than 94.7, which means that kinetic friction prevails. And now you have to draw your system again with your appropriate friction that is going to be kinetic friction. is going to resist in this direction. You have here Fk acting in this way, which is equal to mu k times Fn. So now if I did Newton's second law, I would have 300 minus 50t sine 15 minus Fk, that is mu k Fn. This is along x, which I'm going to say is I hat, plus Fn minus 50g cos 15 j hat is equal to 50x double dot I hat. We had actually found this earlier to be equal to 473.8 newtons, which was obtained by setting this equal to 0. And from this, you can then obtain your x double dot. This here is equal to 0. 50x double dot is equal to this entire thing here. You should obtain x double dot is equal to 2.04 I hat meters per second square. Okay, what is the case? The next case is where P is equal to 0. So now the net force along X is, you can get minus 127 newtons. This here, in terms of magnitude, it is greater than this, which again means that you will have kinetic friction, except now the direction is going to be different. So now the net force is actually acting in this direction, because this does not exist. And so this block has a tendency to slide downward, and you then have the kinetic friction resisting that in this direction. This here is Fk. Now, if you go through the motions, you will have minus 50g sine 15 plus Fk, which is mu k times Fn is equal to 50 x double dot. And from this, you will get x double dot is equal to minus 1.12 meters per second square. To be consistent, I do it this way, I hat meters per second square. All this means is that your acceleration is not in this direction, it's in the opposite direction. Okay. I hope this makes sense. So the first case, your force was such that, well, the net force acting along the slope was such that it would not be able to overcome that static friction maximum force. And so the static friction in this case would be acting in this direction so that it can resist this 23 newtons. So it'll actually match the 23 newtons. 23 newtons being in this direction, the friction force would be equal and opposite. In the next case, the net force in the upward direction is greater than the static friction limit. Because of that, kinetic friction will prevail and it's going to resist the motion that is going to be upwards. And so you have this relation here from which you get x double dot. In the third case, there is no force, and so it's just gravitational force acting, which is this minus 50g sine 15. And we see that the value of that, which is 127 newtons, is greater than the static friction limit, which means again we have kinetic friction, except now the block has a tendency to move downwards. So you have Fk acting upwards. Okay, let's now do another example wherein you have a slope of 20 degrees. And on the slope is a block, some wheels, again 50 kg. but now you have a cable at an angle of 15 degrees with respect to the slope. And this cable here is attached to a pulley. And from this pulley, it's going horizontally. And there's a force acting on this cable, creating a tension of 150 newtons. And there is no friction acting here. So there is no friction, mu is equal to 0. The question asks you to determine the acceleration of this block if it weighs 50 kgs. It's just a matter of applying Newton's second law. Go ahead and try it yourself. Okay, I'm going to try it myself. So I have this block here and the block there. The kinetic diagram. And this here is the free body diagram. What are the forces? You will have 50g sine 20 acting in this direction and 50g cos 20 acting in this direction. Why is it sine and cos? It's the same as what we had in the previous problem. You have here 20 degrees, and this here is your gravitational force. We're interested in finding out this angle. So this 20, and this here would be 90 minus 20. And because this is 90 degrees, this would be 90 minus 20, giving you the same 20 degrees. So then gravity, you can break it down into components. One is this component here, which would be 50g sine 20. And then there's this component here, which is 50g cos 20. Okay. You have normal force. You have that tension, which is acting at an angle of 15 degrees. So I'm going to break it down into T. So you have this tension here. Now the pulley does nothing, it just changes the direction of the force. And so this tension here will be the same tension here. So it is T cos 15 and T sine 15. In terms of the kinetic diagram, the only direction of motion that's possible is along the slope, so 50x double dot. You then obtain the relations that you need. So if I were to now write down along, let's say that the direction up the slope is nx hat, and the direction perpendicular is ny hat. These are just unit vectors. So I can write Fn plus T sine 15 minus 50g cos 20 along the ny hat direction plus T cos 15 minus 50g sine 20 and x hat is equal to 50 x double dot and x hat. So what is the question? It's asking you for the acceleration. If the question asks you to find out what is Fn, then you'd have to set this equal to 0. You would need that if you have to deal with friction, because friction depends on the normal force. In this case, there is no friction. And so all you have to do is set this equal to that. How is that? That's using a dot product of nx hat. You get then that T cos 15, wherein T is given to you as 150. So 150 cos 15 minus 50g sine 20 whole divided by 50 is equal to x double dot. So all I did is I moved this to the denominator and I substituted t is equal to 150. From this, I get x double dot is equal to minus 0.457 meters per second square. What is the meaning of this x double dot being negative, it means that our assumption of the acceleration being up the slope is not actually true. It would actually have been down the slope. That's all this negative sign means. This here is the next question. You have this Bosun's chair, which is essentially something used when you have your building and you might have seen this, but the window cleaning personnel, they use this kind of a boson chair to allow them to move up and down along the side of the building so they can clean up the glass and take care of the appearance of the building. So that's one example. But a boson chair allows the person sitting in the chair to then um, move the chair up and down the building vertically using their own strength. They'd have brakes to make sure that it doesn't fall. But essentially, the person sitting on the person's chair will be able to pull down, creating some tension. And then this set of pulleys will cause the chair to move upwards. Okay, so the question says the person is able to apply 300 newtons, and you can assume that the person's chair is weightless. So this entire component here, the human and the chair, weighs 100 kgs. Question asks, what is the man's acceleration in this case? Okay, so try this yourself. And it looks like you have to apply the constraint motion, but that's not really true. You just need to see what is the net force that the chair and the human is going to be experiencing, and then apply that, the Newton's second law, to then obtain the acceleration. Okay, I'm going to solve it myself. So this here is essentially what I'm considering as my system. I'm looking at all the forces that this is going to experience. To give myself the ability to draw the kinetic diagram, I'm going to show this here. This is the kinetic diagram, and this here is the free body diagram. So what are all of the forces? The human is able to create tension. Now, when the human pulls down on the cable, the reaction results in the cable creating an upward tension force here. This here is tension. So human is pulling down and the cable, when reaction pulls up, then all of the string experiences the same tension. So this here is going to have one tension upwards, another tension upwards, and another tension upwards. So you have 3T acting over here, right? So this pulley experiences T, T, and T. And as I said previously, if you don't know what are the radii, you can assume that they're all parallel and upwards. So we have 3T and T there. We do have gravitational force that is 100 G. And if I were to assume that the acceleration is upward, then I have 100 y double dot as my acceleration in the kinetic diagram. And now I relate these. So I have essentially 4t minus 100g is equal to 100 y double dot. This is the component along j hat direction. It's given that the tension here is equal to 300 newtons. So 4 times 300 minus 100 times 10 is equal to 100 y double dot, giving you y double dot is equal to 2 meters per second square. And so the acceleration is 2 meters per second square upwards. Okay. In all these cases here, we've been looking at acceleration, which is just along a straight line, whether it's in this case upwards, in this case along the slope, or the same along the slope, or maybe horizontal. In the next few examples, we're going to look at cases where you have circular motion and acceleration that is not just some x double naught in some straight line.